Imagine building a civilization without GPS, without laser levels, without computers. Yet somehow, 2,000 years ago, Rome achieved engineering feats that baffle us today. Aqueducts spanning hundreds of miles, with gradients so precise. Water flowed uphill, roads so straight, they cut through mountains like surgical incisions. Cities laid out in perfect grids, as if drawn by a divine hand. Military camps appearing overnight with geometric precision. An empire that conquered the known world not just with swords, but with something far more powerful: absolute accuracy. But here's the mystery that haunts historians. The secret weapon behind Rome's precision wasn't magic. It was a single invention, a surveying instrument so sophisticated, it wouldn't be matched for over 1,000 years. And then, it simply vanished. This is the story of the Roman Dioptra, an instrument that reshaped an empire, then disappeared from history, taking its secrets with it. For centuries, engineers stared at Roman monuments, asking the same question: how did they do it? When Rome fell, it didn't just lose territory, it lost knowledge. Libraries burned, engineers died, and the tools that built an empire were melted down for scrap metal. The Dioptra became a ghost, mentioned in ancient texts, but never seen again. For 1,000 years, humanity regressed. Medieval builders couldn't replicate what Rome had achieved. They watched aqueducts crumble, unable to repair them. The Dark Ages weren't just political, they were technological. We had forgotten how to see. Today, scientists are racing to solve this ancient mystery. By studying fragments, ancient texts, and the monuments themselves, they're piecing together how the Dioptra worked. But the question remains: why did such a revolutionary tool simply disappear? In this video, we will uncover the 5 pillars of the Dioptra, how it mastered water, conquered distance, designed cities, and why its disappearance changed the course of human progress. This isn't just about a tool, it's about the fragility of knowledge itself. The first pillar was water. Rome's greatest achievement wasn't conquest, it was plumbing. By the height of the empire, 11 major aqueducts delivered over 300 million gallons of fresh water daily to a city of 1 million people. That's more water per capita than many modern cities. But here's the impossible part. These aqueducts relied on gravity alone. No pumps, no pressure systems. Water had to flow downhill continuously for dozens, sometimes hundreds of miles. The gradient had to be perfect to steep, and the water erodes the channel. Too shallow, and it stagnates. Roman engineers achieved slopes of just 1 inch per 100 feet. That's a 0.02% grade maintained across mountain ranges. This is where the Dioptra became indispensable. Before laying a single stone, surveyors would map the entire route, calculating elevation changes with mathematical precision. The Dioptra allowed them to sight distant points and measure vertical angles to within minutes of arc. The math was brutal. Engineers had to account for terrain variations, underground obstacles, and the curvature of the earth over long distances. One miscalculation and months of construction would be wasted. The Dioptra transformed guesswork into science, allowing them to predict exactly where water would flow before digging the first trench. It was the difference between hope and certainty. When it worked, it was poetry in stone. Water entering the aqueduct in the mountains would arrive in Rome days later, still fresh, still flowing at the exact speed calculated by the engineers. The Dioptra had turned the impossible into infrastructure. Consider the Pont du Gard in southern France. It stands 160 feet tall, crosses a valley nearly 900 feet wide, and maintains a gradient of just 1 in 3,000 across its entire length. Without the Dioptra, this would have been impossible. The bridge isn't just beautiful, it's a mathematical miracle frozen in stone, a testament to what precision engineering could achieve when armed with the right tool. This mastery of water transformed Roman society. Public baths, fountains, and toilets became symbols of civilization. Cities that submitted to Rome gained access to this hydraulic network. The Dioptra didn't just move water, it moved power. But when the Dioptra vanished, so did this capability. Medieval Europe couldn't maintain the aqueducts, let alone build new ones. Cities shrank, disease spread, and humanity returned to drawing water from rivers and wells. The loss of one tool cascaded into the loss of an entire civilization's infrastructure. The second pillar was distance. All roads lead to Rome, the saying goes. But what made Roman roads legendary wasn't just their reach, it was their refusal to bend. Where nature placed mountains, Rome built straight through them. Where rivers blocked the path, bridges appeared overnight. Roman roads were engineering marvels built to last millennia. They consisted of multiple layers of stone, gravel, and concrete, sometimes reaching depths of 5 feet. But the real genius wasn't in the materials, it was in the planning. Before a single stone was laid, surveyors with the Dioptra would map the straightest possible route, calculating sight lines across valleys and over hills with mathematical precision. The Dioptra turned road building into a military operation. Surveyors would establish a baseline, then use the instrument to project that line forward, mile after mile. Obstacles were noted, but the line never wavered. This wasn't just efficiency, it was strategy. By the empire's peak, over 250,000 miles of roads connected every corner of Roman territory. A message could travel from Rome to the English Channel in just 7 days, a speed that wouldn't be matched until the invention of the telegraph. This network wasn't just infrastructure, it was the nervous system of an empire, and the Dioptra was the tool that made it possible to plan routes with such precision that many are still in use today. Every 1,000 paces, a milestone marked the distance to Rome. These weren't just markers, they were promises. Promises that the road would continue, straight and true, all the way to the capital. Promises made possible by an instrument that could see further than the human eye. These roads moved more than messages, they moved armies. A legion could march 20 miles a day on Roman roads, arriving at the battlefield fresh and in formation. Enemies couldn't hide, couldn't ambush, couldn't escape. The Dioptra had weaponized geometry. When the Dioptra disappeared, so did the ability to build straight roads. Medieval paths wandered around obstacles, following the easiest route rather than the shortest. Travel times tripled, trade slowed, the empire's arteries hardened and clogged. What took Rome 7 days to traverse now took a month. The loss of precision meant the loss of connection, and without connection, empires crumble. Even today, highways across Europe follow routes first surveyed with the Dioptra 2,000 years ago. The instrument is gone, but its vision remains, carved into the landscape itself. Rome's roads outlasted Rome. The third pillar was order. Rome didn't just build cities, it designed them like machines. Every street, every block, every building lot was planned before the first foundation was dug. This wasn't organic growth. This was urban engineering on a scale the world had never seen. Every Roman city followed the same blueprint. 2 main streets, the Cardo running north-south, the Decumanus running east-west, intersected at the Forum, the heart of civic life. From this cross, a perfect grid extended outward. But achieving this precision required more than vision. It required the Dioptra. Surveyors would establish the cardinal directions with astronomical observations, then use the instrument to project perpendicular lines across the entire site. The process was methodical. First, the surveyors would find the center point and establish the main axes using the Dioptra's sighting mechanism. Then, using the instrument's built-in right angles, they'd project the grid outward. Every block was identical, every street perfectly parallel, but the Dioptra's influence extended beyond city walls. Rome conquered farmland using centuriation, a system that carved the countryside into perfect squares, each 2,400 feet on a side. Property lines were surveyed with such precision that disputes were rare. This wasn't just land management, it was social engineering. The Dioptra transformed chaos into property, and property into power. Farmers knew exactly what they owned, and Rome knew exactly what it could tax. Walk through Pompeii today, and you're walking through a Dioptra's vision. The streets are so straight that you can see from one end of the city to the other. The blocks are so uniform that you could navigate blindfolded by counting intersections. This precision created efficiency. Fire brigades knew exactly which streets to take. Aqueducts could be planned to serve every neighborhood equally. Sewers flowed downhill by design, not accident. The Dioptra had turned urban planning from an art into a science. When Rome fell, cities forgot how to be cities. Medieval towns grew organically, streets twisting like tangled roots. It wasn't until the Renaissance that European planners rediscovered Roman principles, but they lacked the Dioptra, so their grids were approximations, not perfections. The instrument that had once organized millions of lives was now just a legend mentioned in dusty manuscripts, its mechanics a mystery. Yet the Dioptra's legacy lives on. Every modern city grid, from Manhattan to Barcelona, echoes the Roman obsession with order. We've reinvented the tool, but we're still following the blueprint. The question is, what else did we lose when the Dioptra vanished? The fourth pillar was the machine itself. So how did the Dioptra actually work? Imagine a telescope married to a protractor, mounted on a tripod, with the precision of a Swiss watch. But this was built 2,000 years before Switzerland even existed. The Dioptra consisted of several ingenious components working in harmony. At its heart was a rotating disc marked with degrees, allowing surveyors to measure horizontal angles with incredible accuracy. A water-level acetyl tube partially filled with liquid ensured the instrument was perfectly horizontal, compensating for uneven terrain. Sighting tubes, like miniature telescopes, allowed the operator to target distant landmarks with precision. Building a Dioptra required master craftsmanship. Bronze had to be cast and machined to tolerances of fractions of a millimeter. Gears needed to mesh perfectly. The water level had to be sealed against leaks. One flaw, and the entire instrument would be useless. Using the Dioptra was an art. First, the surveyor would set up the tripod and level the instrument using the water tube. Then, he'd sight a known landmark and rotate the alidade to measure the angle. By triangulating between multiple points, he could calculate distances, elevations, and gradients without ever leaving his position. It was trigonometry made physical, mathematics you could touch. But the Dioptra didn't work alone. Surveyors operated in teams, using signal flags and measuring rods to establish sight lines across impossible distances. It was a choreography of geometry, each person a node in a network of precision. We know about the Dioptra primarily from one source, Heron of Alexandria, a Greek engineer who wrote a detailed manual around 50 AD. His text describes the instrument's construction and use with mathematical precision. But here's the tragedy: Heron's manuscript survived only in fragments, copied and recopied by medieval scribes who didn't understand what they were preserving. The diagrams were simplified, the measurements corrupted. Archaeologists have found fragments, corroded gears, broken sighting tubes, pieces of bronze that might have been part of a Dioptra, but no complete instrument has ever been recovered. It's like finding a single circuit board and trying to rebuild a smartphone. Modern theodolites, the instruments surveyors use today, work on the same principles as the Dioptra. We've added lasers and digital displays, but the core concept remains unchanged. Rome had invented the future, then lost the blueprint. The Dioptra represents a haunting question. How much other knowledge did Rome possess that we've lost? What other tools, techniques, and technologies vanished when the empire fell? The Dioptra is just the one we know about, because the monuments it built still stand, silently testifying to a precision we couldn't explain for over 1,000 years. The fifth and final pillar is the mystery itself, the disappearance. When Rome fell in 476 AD, it didn't just lose territory, it lost its mind. Libraries burned, engineers died in wars, and the knowledge that had built an empire was scattered to the winds. The Dioptra was never mass-produced. Each instrument was handcrafted by specialized artisans who guarded their techniques jealously. When those workshops closed, when those craftsmen died without apprentices, the knowledge died with them. Unlike stone monuments, the Dioptra was made of bronze, valuable metal that could be melted down for coins or weapons. In desperate times, precision instruments became raw materials. Imagine the irony: an instrument that took months to build, that embodied centuries of mathematical knowledge, melted in minutes to make a few dozen nails. The Dioptra's complexity became its death sentence. Simpler tools survived because anyone could make them. Even the written knowledge degraded. Medieval scribes copied Heron's text without understanding it. Technical terms were mistranslated. Diagrams simplified into decorative doodles. By the 12th century, scholars knew the dioptra had existed, but the instructions for building one had become gibberish. It was like reading a computer manual in a language you don't speak, with all the diagrams removed. Without the dioptra, medieval engineers regressed to methods the Romans would have considered barbaric. Roads wandered, aqueducts leaked, cities grew chaotically. The precision that had defined Roman civilization became a lost art, remembered only in the monuments that refused to fall. For 1,000 years, Europeans lived in the shadow of Roman ruins. They couldn't replicate. They drew water from wells while aqueducts stood empty overhead. They walked crooked paths while Roman roads crumbled beneath weeds. The dioptra had become a ghost. It wasn't until the Renaissance that scholars seriously attempted to reconstruct the dioptra. Leonardo da Vinci sketched designs based on Heron's corrupted text. Others built prototypes that partially worked, but they were reinventing from scratch, not recovering lost knowledge. The original dioptra, with all its refinements and secrets, remained lost. We had rediscovered the concept, but not the mastery. Today, we still don't have a complete dioptra. Museums hold fragments, archaeologists debate interpretations, and engineers build educated guesses. The instrument that reshaped the ancient world exists now only in theory, and in the monuments it left behind. The disappearance of the dioptra teaches us a brutal lesson. Knowledge is fragile. It doesn't survive in monuments or ruins, it survives in people, in practice, in continuous use. When the chain of transmission breaks, even the most sophisticated technology can vanish in a single generation, leaving behind only mysteries and monuments we can admire but not replicate. Today, we build with tools the Romans could never have imagined: lasers, satellites, computers. Yet we're still following the paths they laid out with the dioptra. Our cities still align with their grids. Our roads still trace their routes. The instrument is gone, but its vision persists. Modern surveying instruments are direct descendants of the dioptra. The theodolite, the transit, even GPS-based systems all rely on the same fundamental principles that Roman engineers mastered 2 millennia ago. We've added precision and automation, but the core concept of measuring angles and distances to map the world remains unchanged. In a very real sense, every surveyor today is using a dioptra, just one evolved beyond recognition. Researchers continue to study the dioptra not just as history, but as engineering. By reconstructing it, they've discovered techniques and shortcuts that modern surveying has forgotten. Sometimes, looking backward teaches us to move forward. The dioptra's true legacy isn't in museums or textbooks, it's carved into the earth itself. Every straight road, every level aqueduct, every gridded city is a monument to an instrument most people have never heard of. Rome fell, but the dioptra's geometry is eternal. Think about that for a moment. A single tool, built by hand from bronze and glass, fundamentally altered the trajectory of Western civilization. It made possible the infrastructure that sustained millions, the roads that connected continents, the cities that became the foundation of modern Europe. And when it vanished, progress stalled for a millennium. The dioptra proves that technology isn't inevitable, it's fragile, precious, and easily lost. We live in an age that assumes knowledge accumulates, that progress only moves forward. The dioptra reminds us that's a dangerous assumption. Civilizations can forget. Technologies can disappear. What we know today could be a mystery tomorrow. If we don't preserve it, teach it, use it. Here's the final irony. Many of the structures we build today with our advanced technology won't last as long as what the Romans built with the dioptra. The Pantheon's dome is still the largest unreinforced concrete dome in the world. Nearly 2,000 years later, perhaps precision isn't just about accuracy, it's about permanence. The dioptra is gone, but its questions remain. What else have we lost? What knowledge sleeps in ruins, waiting to be rediscovered? And what are we creating today that future generations might have to reinvent from fragments and guesses? Every time a surveyor sets up a theodolite, every time an engineer plans a road, every time a city planner draws a grid, they're channeling the spirit of the Dioptra. The instrument may be lost, but its purpose endures, to bring order to chaos, to make the invisible visible, to transform vision into reality. That's not just engineering, that's the essence of civilization itself. The Roman Dioptra reshaped the ancient world, then vanished into history. But its legacy lives on in every straight line we draw, every level we check, every city we plan. I'm Ethan, watching the past so we can understand the present. I'll see you in the next era.